third day conference, the DESSERT'. And now we will continue our work as fourth plenary session. We have one plenary talk. Sorry, we have information about our second plenary speaker. Please, Dr. Bardis will inform you.
Yes,
Welcome,
good morning.
Nikas.
Good morning. We had yesterday that our colleague Thanos Kakaroudas, Vice Chairman of IEEE Greek section and head of the Department of Informatics for the Informatics of University of Thessalia, he got ill and he couldn't speak from yesterday, and so he can't today. But he will video with his plenary lecture, and we will upload it to our website in a few days. Also, when the first days he was with us, and we see that he was ill, but it was worse, and now he can't even speak at all. So we'll continue. It was a parallel session on that, so it doesn't matter to our program schedule. We have 1 hour for our first plenary session from 10:05 to 11. So we'll continue as our schedule is. Thank you, Professor Hudson. Please.
Thank you, Professor Bardis. Okay, now we have about 1 hour for our plenary session, and it's our pleasure to invite for plenary talk our colleague, Dr. Alexander Ivasyuk. Alexander, welcome, and you can share your monitor for your presentation.
Hello, everyone. Yes, just a minute, please.
I would like to introduce Alexander. Alexander is head of validation department, research and production company RadICS, doctor of science candidate at the Department of Computer System Network and Cyber Security, National Space University. For more than 10 years, Dr. Alexander Ivasyuk has been researching providing green and safe power generation and reducing CO2 pollutions. He was a leader of the validation testing team that conducted comprehensive testing of the digital PLC based on FPGA technology to meet the requirement of IEC 61508 by SIL 3 level in one channel. Such a type of PLC is the core of IC for advanced small modular reactors and modernization of existing power units. Nowadays, Dr. Alexander Ivasyuk is researching the interconnections between safety and security features for the digital PLC. This research result will reduce the time and efforts for estimating the cybersecurity level of PLC based on its safety level. Hence, we have enough time. Alexander, welcome for your presentation.
Okay, thank you, Professor Kachenko. And today I'm going to represent you the presentation which is called as Evolution of Validation Testing Methods and Tool, 10 years of RadICS Platform the SIL 3 certification. The agenda of the presentation you can see now on your screen. The agenda was built in a way which allows to avoid the case when the speaker clearly understands his speech, but for audience it's not clear. And I would like to start from the first topic from agenda and represent the general overview of the RadICS platform. On this slide, you can see the general schema of the INC system. If the INC shall to perform the safety function, for example, to stop some technological process on the plant, this INC will be considered as the safety INC. The core of such type system is the Programmable Logical Controller, PLC, which gathering signal from the different sources, proceeds them, and generates the control commands to actuators and the different annunciation signals. And the main object of the presentation is a safety PLC called RadICS Platform. The RadICS Platform is continuous improvement PLC. Its evolution now is represented on the slide. As showing, this version of the platform accumulated more than 20 years experience of developing, testing, modernization, and operating of the safety PLC and safety system, safety INC system. On this slide, showing the technical nesting of the INC channel based on the RadICS platform. As you can see, the cabinet consists of the chassis, where the different type of modules are installed, and each of the module has their core, its FPGA. If PLC is going to be certified in accordance to 61508 standard, it must meet the following main requirements, which you can see on the slide now. So, the main characteristic of the RadICS platform are the next. The solution is developed 100% in-house, so there is no external IP and no black box. The self-diagnostic coverage is more than 99%. The SIL 3 level in single channel. The safe state is too de-energized to trip. The high density of the input-output channel per module. No available interface for free connections. Certified internal diversity. And the first topic is finished, and now I propose to consider the second topic, the RadICS platform development timeline. Let's discover how the functional abilities of the RadICS platform have been increased along the time. First phase was done in 2014, and platform could get discrete and analog signals and could generate only the discrete output signals. The specific application algorithm should be designed in IDE quarters by using VHDL language. After the second phase, the ability to generate output analog signals was added, and also the optical connection to another chassis by using the proprietary protocol was implemented. And for the possible connection with some, let's say, old INC, the interfaces RC232 and RC485 were added. During the third phase, the fundamental changes have been made. The logic modules, by the way, it's I will say its main module of the platform, where the application algorithms in performing was changing to carry out the application algorithm, which now, comparing with the first phase, now shall be designed by using the specific software tool, which is called RadICS Programmable Configuration Tool. This tool provides a comprehensive ability to visualization and significantly simplified the process of application algorithm creation. Due to RPCT, the developer don't need to have the specific experience of knowledge development algorithm in VHDL. And this set of hardware and software equipment was firstly evaluated by the US NRC, was successfully evaluated. After the first phase, the platform got ability receiving the thermocouples and RTD signals, and the range of analog signals was increased, and it's equal from minus to plus VDC. And as you can note, this updated set of hardware and software of the RadICS platform was evaluated successfully second time by the US NRC. During the first phase, the platform and the RPCT got the updating to perform different testing of the application algorithm before this algorithm will be implemented into the system. If we look at the platform from hardware and software configuration, we will get the pictures that's shown on the slide. At the beginning, the platform consists of logic module, discrete input and output modules, and analog input modules. Then, the analog output modules and optic communication module were added. After third phase, the hardware design of the logic module was updated and RPCT software tool was added. This hardware configuration, as I said before, was evaluated by the US NRC. Then the thermocouple input module and RTD input module were added, and to operating in the spreading analog signal range was added wide range analog module. At the same time, the modules analog input and analog output were updated. After first phase, the ability to make the different testing of the application algorithm by means of RPCT was added. The hardware configuration, on the other hand, left the same. The full set of RadICS platform module is represented on the slide. From the first phase, we got 4 modules. Then 2 more modules were added, and the finally set at the current module at the current moment of the RadICS platform module is 9. As it mentioned above, in the first phase, 2 existing modules got some updates. On this slide, you can see the difference between the time is taken to develop the modules and needed time to update them. This became possible by using stable developing and testing process and appropriate technology.
Dear colleagues, good day. This session is not
The
possible
second
because
chapter is finished,
presenter
and
is ill.
the new part of the presentation, I would like to start by representing starting testing when the firmware, I mean platform software and hardware, are integrated together into the module.
Andrei, do you hear me?
Demand careful testing management to check all of the design requirements, and the test shall full cover the requirement. Testing of the safety programmable devices imposes additional requirements, for example, to verify the specific features such as self-diagnostic coverage or reaction time of the system. The decision-making on the independent certification body regarding the system is well based on the studying the testing documentation. On this slide, shown the photo, the test specimen before starting qualification seismic testing in the Kinetrics lab, which is located in Canada. How can the self-diagnostic coverage be proved? There is only one way, is to perform fault insertion testing. What does it mean? It means that the module should get the single hardware fault, and after the fault had been activated, the tester must record the obtained result and compare them against expected results. The general sequence of fit performing is shown on the right side of the slide. But how it can be implemented in real life? If you have the new idea, you have to get the proof of concept. On this slide, you can see the first proof of concept. And you can note how messy loops wiring connection for this type of testing was developed the special device. But despite this, despite its appearance, this approach has allowed us to be confident that model detecting each inserted fault. Let me ask you to remember how general wording has the expected result. It will be needed further in the presentation. We tried to improve our approach, and the second proof of concept you can see now. This tool allowed to combine discrete and analog faults. Also, this device could display the inserted type of fault, and the wire connection becomes look better. And there is one more detail, that previous device connected directly to the modules, but the second one device got the cable, and it provided to tester some freedom of movements. Along the old certification way, our intention was to make testing more closely to real operation condition. That's why another approach to performing the fault insertion testing was made. This approach helped to not use a special device, because all needed switches are located directly inside the directly beside the module, near the module. This approach helped not use the special device, as I said, and it was for tester, it was much easier and more comfortable to conduct the test. As a result, we could perform testing when the several modules at the same time were installing into the chassis, and any combination of the faults could be activated. Documentation. Documentation is a challenge which faces the team along the certification process. Especially young colleagues suffering when they have to work with the documentation, because this process is quite boring, let's be honest. Each testing activities has separate set of documents, such as plan, specification, and report. The one of the hundreds of the test cases you can see on the screen. Please take into account how detailed the expected result is presented in this case. Each test step has a particular expected result. So this is the expected results, and this is the sequence of test steps. Each of the test steps has own expected results, and the tester, when the first, the second, the third test steps is performed, the tester clearly know what the reaction of the test object should be. And its test reports, the tester recording all obtained result for each test step. So we can see the expected and actual result, expected result, actual result for test steps 1 and 6. This we can see the expected result and actual results of for the steps 2 and 5. In the bottom line, we can see the results of third test step with some photos, and the test step number 4 also has been recorded the actual result, and as one more argument of the credibility of this test, we put it the photos so frequently making the test description and it documented takes more time than test performing. All tests are divided on the two large groups. It's a functional test and the analytical test. On the previous slide was represented the functional test. Analytical test is a type of test when the tester shall to analyze something. It could be the test reports from the previous stage, it could be the supplier documentation, or it can be the design documentation. The example of such test is displayed on the slide. As you can note, it also has detailed description, and another example of analytical test now you can see is the example where the constructor documentation should be analyzed before module will be manufactured, and after module is manufactured, the tester also compare and also analyze what type of the units module consists of, and it lead that requirements from the hierarchical design documentation 100% implemented into the real module. On this slide, the first test bed are represented. At the beginning, the most of the tests were made manually, despite on using equipment from National Instrument Company. One of the hardest tests, it was the estimate response time of the PLC. Other words, to estimate how much time taken on the reaction of the platform. And this test was performed manually by using digital oscilloscope LeCroy. But the numbers of modules and parameters that have to be checked and monitored simultaneously are continuously increased. And of course, the validation team did not have any other choice than go to automated testing. On this slide, one of the latest test bed is shown, where the specific test software and hardware equipment of the third part was using to set test inputs and to make the registration of outputs. During the qualification testing, all tests are performed in special negative environment condition. So, even response time testing was performed automated by using software which are working without operational system. And the example of test reports of this test now is on your screen. Why we should to avoid and not to use the operational system? Because operational system get impact to the time and the additional milliseconds could be added to the test. At the current moment, the maintenance and diagnostic cabinet was developed and manufactured for performing the full automated testing for each type of the module, with testing all the parameters, all the functions and parameters. And we finished the third part, and let's consider the last but not the least part of the presentation. Theory and practice are two halves of a whole. Theory is proved by practice. And the RadICS platform was evaluated by the different independent bodies. Firstly, it was IEEE company. I have to note that IEEE company did it continuously along the developing way. Secondly, it was US NRC, Nuclear Regulation Commission of the United States, which gives the permission of the using RadICS platform in safety INC on the US nuclear power plants without any limitation. Unfortunately, Ukraine had a unique experience. Our NPPs and INC system, INC equipment were tested in raw condition. This slide demonstrates the sequence of action taken by safety system based on the RadICS platform. All action have been made without human interaction. And let me give some comments regarding this slide. Firstly, when the three power lines of 330 kilowatts were lost because of missile attack, the system made the decision to discharging two power units from 1,000 megawatts both, each of them, to approximately 500 megawatts. When the lost another one power line, 750 kilovolts, again by the missile attacks, the reactor chip system generate the signal to stop nuclear reaction. This control command called SCRAM. And the INC system puts the command to activate diesel generator. And once the two backup power lines of 330 kilovolts were backup, the diesel generator got the command and stopped. So it's important that all this action have been done without operator interaction, because we have no doubt that operator performing their duties as needed, as required. But operators are humans, and they have the family, and they don't know what in this particular moment happened or where their family. So it's important. I said one more time that it's important that all this action have been taken without human interaction. If we are talking about the USA nuclear industry and nuclear market, two projects related to advanced small modular reactor decided to build their safety INC system on the RadICS platform. And you can see that this both project performance the TerraPower company, No, maybe you know that owner and owner of the TerraPower company is Bill Gates. And additionally, one of the modernization project of the existing NPP also chose the RadICS platform to perform modernization project of the existing safety INC. Such a large amount of practice could not have been accompanied without scientific achievements. There are three main scientific areas which I propose to consider. First one is models and methods for analysis, synthesis, and providing the safety, security of multi-version systems. And the second one is modeling and probabilistic assessment of the safety critical INC system. Practical values and human achievement, I would say, now represent on this slide. And to be clear, it's this scientific achievement, it's not part of the, I would say, it's not only the part of the validation team. No, it's all group of the people who have some relation to the SIL'3 certification process. And the next slide shows the scientific area number 3, the verification and validation methods and the supporting of the certification process. And the hot research topics is multi-feed models and methods, safety-supported assessment of security, strategies, models, and methods of online verification testing for cost-efficient, safety-critical INC system. And in the end, I would like to share with you some curious metrics related to the validation team's scope of work. For more than 10 years, were created and updated 84 documents. 5,118 tests were designed and performed. And the total number of pages approximately is 16,952. So I represent just one part of the certified process. There are design and verification parts. These parts have their own history. What the validation team plan on the next phase? First of all, we intend to improve the fault insertion test approach, and we intend to combine the fault insertion testing and the penetration testing. Even though the standard 61508 has nothing to say about cybersecurity, but real life dictates their own rules. And secondly, based on the national instrument equipment, create the model of the real technological process and connect it to PLC. We realize that this could be done with some limitation, but it will be another step from the testing in the test area to testing in real condition. Thank you for your attention, and I'm ready to answer on your question, of course, if you have such question. Thank you.
Thank you very much, Alexander. And we have time for questions and discussion. Welcome for your question, dear colleagues. If it's possible, I ask you, Alexander, about security issues. You talk in your presentation about this topic as more future activities. But one of the your slide was dedicated to safety and security relation. And what about specific particularities of PLC-based INC for such object as nuclear power plants or small modular reactors in point of view security and safety? We know that these kinds of system are close in context of general cyberspace. Hence, what about your opinion concerning this issue? Is there any challenges in this area for such kind of systems?
Thank you for your question, and I will try to answer. The INC system, based on the, for example, for the RadICS platform, is some specific system which does not have any free connection. I mean, there are no USB interfaces, and there are no some Wi-Fi interfaces or Bluetooth interfaces. No. All connections and all interfaces covered by self-diagnostic. It means that, for example, if we set the configuration of the particular chassis, and in the configuration we define what type of module should be installed in some specific slots of the chassis. And if someone got the physical connection and try to change the slot of the modules, the system can detect it. And for example, if we will try to cut the interfaces of the data transferring, which located inside the chassis, or as I said, we have the, for example, optical communication module, which could connection with another chassis with another optical communication module, and if this connection will be disconnected, or some main, I will say, main inside will try to insert it on this connection. The platform also detected, and such type of tests were performed during the SIL3 certification process. Because if we are talking about more than 99% of self-diagnostic, it means that any deviation of the hardware unit, behavior of the hardware unit, includes the FPGA, are continuously monitoring, and if such cases happen, the self-diagnostic detects them, and this depending of what type of fault was detected, the system will go or to the safe state, de-energized to trip, or the annunciation signal will be generated and displayed on the information board unit. So, and this why for this type of system, I think it's possible to evaluate security features by based on the existing test reports, for example, fault insertion test, or maybe some requirement from when the whole chassis has been tested. And it's possible to build the connection, to build the bridge between safety features of the such type of system and security features. Yes, I think it's possible. If we are talking about the safety system which have the less percent of self-diagnostic coverage, I'm not sure that we can build such type of bridge. Maybe we can get some connection between safety security, but when we coverage, okay, how we protect the computer, our personal computer, against the cybersecurity threats by using some diagnostic software. It's antivirus software, different type of antivirus, and there this antivirus is continuously making self-monitoring of the health of the PC, what the input signals comes to the PC, and makes the decision: is it a virus? Is it some spam or something like that? But in this, in our case, the system has their own self-diagnostic, and I would say full coverage self-diagnostic, and this is something like umbrella that could be help to achieve and safety features of the platform and security features also. This is my point of view on your question.
Thank you very much for your wide and interesting answer. Dear colleagues, have you any other questions? Welcome, Alexander Gerasin.
Thank you very much for your work. It is very important and high quality. So I want to ask you, what software tools can you recommend for developing and teaching the development of FPGA-based devices in according with your experience?
Okay, thank you for your questions. You know, it depends on the goal, what you are going to achieve. If we are talking that you would like to build safety system, there is some specific procedure that should be performed before you start the developing process. And according to this procedure, you have to evaluate the potential software tools which is you are going to use for your development process. And it depends on, for example, if we are talking about the, again, as a safety application, we are trying to make this process by not using existing, I would say, black box IP core in FPGAs, or if you don't have any other way, as you should use this IP core, you have to evaluate that you have to know if this type of FPGAs and IP core have such type of certification is called safety case. This type of certification conducted by the supplier of the FPGA, and this package, safety package, allow to use some specific FPGAs and some specific IP cores in safety development process.
Okay, thank you.
Thank you.
Thank you. Then next question, Konstantin Leontiev. Welcome.
I would not like, good morning, everyone. Good morning, dear colleagues, dear participants. I would not like to ask Alexander, but I would like to add and answer the question from Alexander Heras. So if you are talking about the students, about the university, about the teaching process on the field of FPGA programming and experience using of FPGA, then I would like to say that first of all, you do not need to bind to particular FPGA and software. Of course, every FPGA family configuration needs to be done in the special IDE software provided by the FPGA manufacturer. Okay, it's clear. So, for example, for Altera Intel FPGAs, it should be Quartus software. For Silence, another one, and so on. So my suggestion is do not bind to this software directly. So do not use graphical methods of creation of FPGA configuration, rather to use raw code. So for this, you can use any software to write the code, then create your own projects within and just use software IDE software provided by the manufacturer, just to compile the project, just to perform some additional important task like time analyzing or debugging and so on. And for example, for verification, I suggest to use independent software, of course, so not provided by the manufacturer. And again, my advice and my suggestion: do not bind to the manufacturer software. And the set point is cybersecurity issues and independent verification. So in this case also, and using such approach, you can easily migrate between families. If you, of course, will not use IP cores provided by the manufacturer, and you can show your students, for example, how easy the process of migration is between the families of the same manufacturer or between the families, FPGA families of different manufacturers. So this is my comments, and thank you.
Thank you, Konstantin.
Thank you for detailed answer, Konstantin.
Thank you for your comments, Konstantin. And any other questions or comments? Okay. Thank you once more, Alexander Ivasyuk, for your very interesting talk, for representation of these industrial results. I think we understand that it's very interesting, very hot direction, because safety and security of energy grid, nuclear power plants, and so on, is very important for safety and security in general. Thank you.